Welcome back to our Chem 152 video series. In this video, we'll find the binding energy of the nucleus of an atom. This question gives us the atomic mass of sodium-23. Note that it is not exactly 23, but slightly below. We are then given the mass of a proton, neutron, and electron, and we are asked to find the mass defect in AMU. In order to find the mass defect, we're going to have to add up all the masses of all the protons, all the neutrons, and all the electrons. I've given you the symbol for sodium above. Sodium-23 has a mass number of 23 and 11 protons. I'll represent the protons with the letter P. And then to find the number of neutrons, we take the mass, 23, and subtract 11 to give us 12 neutrons. Also, we will assume that this atom is neutral and therefore the protons and the electrons will be the same, so we'll have 11 electrons. Now we'll make a table to help us sum all of the masses up. We'll first list the numbers of protons, neutrons, and electrons. There were 11 protons, 12 neutrons, and 11 electrons. Now we'll write the masses of each one. We'll copy our numbers given for the mass of protons, neutrons, and electrons. Now we'll multiply the number times the mass for each line. When we multiply the first row, we will get 11.0800415. This will be in AMU. When we multiply the second line, we'll get 12.10395. For the third line, we'll get 0.006495. Then we will add all of the masses together. Once we add all the masses, we will get 23.190421 AMU for the total. Now to find the mass defect, we'll take the total mass minus the atomic mass. We'll copy our total mass from the previous step, where it says total here, and we'll subtract the atomic mass we were given above. When we subtract, we will get 0.200651 AMU for our mass defect. We can label this as delta M. That will stand for mass defect. We'll carry that mass defect forward into the next part of the question. Now that we have our mass defect in AMU, we can convert to kilograms. We'll begin by getting out of AMU by placing it on the bottom of a fraction and getting into grams first. Then we'll multiply by another fraction to take us out of grams and into kilograms. 1 kilogram is the same as 1,000 grams, and 1 gram is the same as 6.02 times 10 to the 23rd AMU. Therefore, we'll start with our mass defect from the previous step and multiply it times both of these fractions. If we put this in a calculator, we will get 3.333 times 10 to the negative 28th kilograms. Now we'll carry forward that mass into the next step for part C. Part C asks us for binding energy in joules, and the binding energy, E, is equal to mass times the speed of light squared. We'll use our mass from the previous step, and then we'll multiply that times the speed of light squared. The speed of light is a constant, 2.998 times 10 to the 8th power. We'll square that and multiply that by our mass defect in kilograms. When we multiply in a calculator, we'll get 2.996 times 10 to the negative 11th joules. Our final step for part D is to bring forward that amount of joules and change it to electron volts. We'll multiply by a fraction to take us out of joules and into electron volts. And 1 electron volt is the same as 1.062 times 10 to the negative 19th. This is another conversion that you may not know, but you could look it up if you needed it. If we do this multiplication in a calculator, we will get 1.87 times 10 to the 8th electron volts. And so this is how we use the mass defect to find the binding energy in our nucleus of sodium. Thank you for watching. We'll see you again soon.